All right, hi everybody. Welcome back from lunch. We're going to get started with our next session, which I should remember the title of, which is called Mesoscale and Sub-Mesoscale Physical, Biological, Biogeochemical Interactions. And for this session, we are going to be picking up from the last session. We're still talking about natural perturbations in the system, but just at a much smaller scale. And so we have 5 speakers, and we're going to start out with some of the dynamics and processes of physical and biological interactions, and then go into some of the chemical signatures of these features, and then we'll end with the who's doing this stuff, the actual organisms in there that are doing things. And so we'll start off today with Peter Gaube, and he'll be speaking about, his talk title's right up there, Mechanisms of Mesoscale Physical Biological Interaction, and he is coming here from APL at UW.
Thank you, and thanks for this opportunity to share some of the work we've been doing here for about the last decade. So what I'll do today is give an overview of the different mechanisms we've sort of identified to apparently play a pretty important role in mesoscale modulations of primarily chlorophyll. And this is mostly done from a satellite perspective, and then we've used a Eddy resolving physical biological model to sort of do a bit of hypothesis testing. And if the lights were off, you could see a very beautiful picture of Eddy from the Alaska stream there, just a little southeast of Kodiak Island. And this is just, one of these beautiful realizations. What I really like about this, and what I hope you guys take away, is the things I'll talk about is on the scale of that whole Eddy. But you'll see so much excitement and movement happening at these much smaller scales. So today we'll start at this mesoscale, order 100-kilometer features, and we'll move all the way down to the sub-mesoscale. So mesoscale eddies are, well, for one, they're ubiquitous. So what I'm showing here is sea level anomaly, and the black lines are eddies that are identified and tracked in an automated procedure. What we can notice from this is that the amplitude of the eddy is shown in the colors, with reds being anticyclonic eddies with positive sea surface height signatures, blues and purples being cyclones. The amplitudes are generally intensified in western boundary currents, along different fronts in the Southern Ocean. You'll also notice in terms of propagation, once an eddy sort of leaves a boundary current, it's able to propagate just due west. And that can be quite important because these eddies are, in general, especially outside the tropics, highly nonlinear. What that means for us is they trap these large masses of water, and they can transport them over thousands of kilometers. So what we'll do is we'll look at eddies, and we'll look at it in sort of a Lagrangian frame of reference, where we use these tracks to co-locate all kinds of different observations to kind of tease out the mean signature of the eddies on chlorophyll and other parameters that we can observe from satellites or reproduce in global models. I know we want to watch that again. So this here is what I like to call our roadmap, and this is simply the cross-correlation of chlorophyll anomalies with sea level anomalies. So one thing we notice right away is that we have regions of positive cross-correlation, and that means we see elevated chlorophyll associated with anticyclonic eddies, which have positive sea surface height perturbations. And we see regions of negative correlation. You can sort of pick out that the western boundary currents are generally negatively correlated. Large swaths of the subtropical gyre are positive. And then there's a region in the South Indian Ocean that I find quite interesting that's positively correlated. And we're going to go into detail on a couple of these different regions. But first I want to talk about some of the different mechanisms. The first mechanism I like to mention is the trapping of ecosystems by these eddies. So eddies are generally nonlinear. They're rotating faster than they're propagating, so they can actually trap phytoplankton and full ecosystems within their interior. This is shown very nice in the simple schematic where we have the Gulf Stream, we have a meander that eventually becomes unstable, and in the case of an anticyclonic Gulf Stream meander, we trap a parcel of water that originates from the Sargasso Sea. That eddy spins off, becomes its own feature, and now you have this ecosystem from the Sargasso Sea propagating through the slope water. So you can imagine that generates quite large gradients both in the physical field and very much so in the biological field. Furthermore, it helps to inhibit exchange across the boundary of the eddy, so you can imagine that you have sort of a unique evolutionary system or adaptation system happening within the interior of these eddies. So that kind of allows us to do some different almost sort of case studies in looking at eddies in a region where the water inside an eddy is quite different than its surroundings, so we kind of expect very different perturbations. So one mechanism by which eddies influence biological ecosystems is the trapping. So that's just trapping and horizontal transport. So by doing this Lagrangian analysis, we can sort of look at the evolution of the chlorophyll signatures of eddies following the eddy. And so for the case of trapping, here are just some idealized composite averages. So I'll show a lot of these throughout the talk. And so what we're looking at here is the average picture of what an eddy looks like with the center of the eddy here. The x and y axes are scaled by the radius of the eddy, so it's sort of a normalized coordinate system. And for the case of trapping in like a western boundary current, like the Gulf Stream off the coast here, we expect to have high chlorophyll water in cyclones, and that's from the entrainment of slope water. And as I showed earlier, we'd expect low chlorophyll water in anticyclones coming from the Sargasso Sea. Now, another thing we can do in this sort of analysis frame of reference is look at what happens to the time series, or so the evolution of chlorophyll inside an eddy from when we first form an eddy to when we first detect it using the altimetry systems we use, during the intensification, maturation, and eventual demise of an eddy. So for this first mechanism, the trapping, if that is the only mechanism that is actually influencing the chlorophyll in eddies, so in an idealized world where nothing else is happening, we wouldn't really expect the chlorophyll signature to change much. And as we go through the different mechanisms analysis, we'll look at these sort of time series and these spatial structure plots again and see how different mechanisms change those. The next thing I'd like to talk about is the horizontal stirring of chlorophyll. And I skipped a slide there because they're in the wrong order. So this is some work we did back in 2011, both with Dennis and Dudley Chelton, and we looked at this region in the South Pacific where a lot of work had been done in the past looking at westward propagating features of chlorophyll, and for the longest time they were attributed to linear Rossby waves. And with the advent of higher resolution altimetry, we started to see that when we look at the chlorophyll field shown here, this is a snapshot of chlorophyll, and we overlay the eddy fields, we see these perturbations appear to be quite correlated with the eddy field. And so what we did is, again, we tracked everything in that region and we created these composite averages, and we went through and looked at what does the mean signature of the eddies look like on the chlorophyll field in this region. So for the case of clockwise rotating eddies, we see low chlorophyll anomalies on the leading edge and high chlorophyll anomalies on the trailing edge. And what we believe generates this is basically the stirring of a gradient around the eddy. So if we go back one slide and just look at what the mean gradient looks like in this region, we can see that we have low chlorophyll to the south and high chlorophyll to the north. So the case of a clockwise rotating eddy, we're bringing low chlorophyll from the south up here, generating a negative anomaly, and high chlorophyll from the north down here, generating a positive anomaly, and vice versa for counterclockwise rotating eddies. So when we see this sort of dipole pattern in chlorophyll anomalies, we attribute that to the horizontal stirring of chlorophyll by the eddies. And so this is just shown schematically here. What I just explained is if you had an unperturbed background chlorophyll gradient shown by the dashed line here, the rotational velocities of the eddies will move that gradient downwards in this case here where we have high chlorophyll to the north, low chlorophyll to the south. And one more thing I want to point out is that there's an asymmetry to this. There's the leading anomaly generally is larger in magnitude than the trailing anomaly, and we attribute to the fact that these westward propagating eddies are encountering a previously undisturbed chlorophyll field, so they're able to create a larger anomaly on the leading edge, whereas the trailing edge is actually advecting chlorophyll that has already been disturbed by the eddies. So it just makes sort of a smaller anomaly because it's kind of already been stirred together. When we did this globally, when we took all the eddies in the mid-latitudes, composite averaged them together with over 100,000, not only individual realization, but 100,000 long-lived eddies. So these are eddies with lifetimes greater than 12 weeks. We see that this dipole pattern emerges again, especially if we take our observations and we rotate them so that we have either a northward or a southward chlorophyll gradient. So from this, we determine that on a global scale, when we look at eddies that have radii of 100 kilometers. So this is the mesoscale. This doesn't include submesoscale. We've smoothed all that away. The dominant mechanism by which eddies influence the chlorophyll field is the stirring of ambient gradients around the eddies. And you can see that if we look for the southward gradients, we get the same pattern we expect with the dipole that is explained by the direction of the gradient relative to the rotation of the eddy. The next mechanism I want to talk about is we've moved away from the horizontal stirring and trapping, and now we're going to talk about vertical fluxes. And this is sort of the quintessential mechanism by which we are all taught how eddies influence ecosystems. This is what we call eddy pumping, or the uplift or pushing down of isopycnals during the formation or intensification of eddies. So for the case of anticyclones, when we form an anticyclone intensify, we push isopycnals down. this would be expected to take water from the euphotic zone, push it down, and therefore really not having much of an ecosystem response, or if anything, pushing live phytoplankton cells out of the surface lit ocean. In the case of a cyclonic eddy, we have the upwelling of isopycnals. So now we've heaved isopycnals up, we've put new nutrients in the euphotic zone that can be utilized, and as we saw in the student presentations earlier, there's multiple ways in which those nutrients are actually upwelled. It's not just the heaving, but we also have the transport along isopycnals. So as I mentioned, this is sort of a very quintessential eddy mechanism. It was actually observed quite early on in terms of chlorophyll data. So here we have an example of two different cyclonic eddies, which are characterized by cold water. Again, that's from the upwelled isopycnals, right? Cold upwelled water, and high chlorophyll. So in regions where we have this mechanism, this eddy pumping or eddy intensification mechanism occurring, we'd expect high chlorophyll in cyclones. And this would lead to negative correlation from that roadmap I showed earlier. That's all I really am going to say about this mechanism, because I'm going to focus on one that's a little newer and that we've done quite a bit of work on recently. And that is a different mechanism that drives upwelling in eddies, and this is due to the interaction of the surface currents with the wind. So in the ocean, when you blow a wind over the ocean, the wind that's actually forcing the ocean is relative to the ocean current. So what does that mean? Let's think about in the case of the Gulf Stream. Say we have a Gulf Stream moving due east at a meter per second. If you blow a wind in that same direction, the ocean itself has no wind stress because the relative motion is zero. So now let's think about a rotating eddy. So here we have a diagram of a rotating eddy. So this is a northern hemisphere anticyclone. And then we blow a wind over it. Okay? In the region where the wind is going in the same direction as the current, we have a reduction in the wind stress. In the region where the currents of the eddies oppose the wind, we enhance the wind stress. This induces a curl in the wind field and therefore Ekman pumping. So we have a net divergence. So in anticyclones, we have upwelling. It turns out that no matter where you are in the world ocean, when you have an anticyclone and some sort of ambient wind, you will create upwelling in the Ekman layer or the surface layer of anticyclones. This was shown to be very important for biogeochemical processes by Dennis and others during the Eddy's field program around 2005, where they went through, they found a large anticyclonic eddy that was in the northern Sargasso Sea. They sampled it with a towed instrument, and they found a very, very large diatom bloom in the center of this anticyclone. Now, in general, anticyclones in these regions are characterized by very low surface chlorophyll, and this eddy itself was characterized by low surface chlorophyll. But at the base of the euphotic zone, they saw very high perturbations of fluorescence related to the diatoms they were able to identify from the imaging instrument. And indeed, they found that it was multiple standard deviations greater than the sort of standard chlorophyll profiles they get from bats, which is close to this area. So they found a very large bloom. They did a tracer experiment, and they were able to measure upwelling velocities that were very consistent with this Ekman pumping that's induced by eddies. So today I want to talk a little bit more about surface current-induced Ekman pumping. And I promise this will be a very simple differential equation to go through. So as I mentioned before, we have a wind field. And at the center of that wind field, we have an eddy. And here again, we have the case of an anticyclone. The relative wind, which is what forces the ocean surface, is the wind field minus the ocean currents. When we do that, we see that even in a uniform wind field, we end up getting this curvature. So this curvature is a curl in the wind stress. We know that Ekman pumping is a function of the curl of the surface stress, or the wind stress. So when we carry out this derivative and we do manipulate a little bit, we can actually look at the different terms that are important here. So if we carry this out, we see the first term comes out. This is your standard Ekman pumping term, and this is the surface current-induced Ekman pumping. This is, turns out to be sort of the dominant form of upwelling induced by the winds and eddies at the mesoscale. There's a second term here that's quite important, especially when we get to smaller scale. We name this the vorticity gradient-induced Ekman pumping, and this has to do with the interaction of the gradient vorticity of the eddy with that of the surface stress field. And as we get to smaller and smaller scales, so as we approach eddies with diameters of order 10 meters, this becomes the dominant term, and we start to get upwelling velocities that can exceed multiple meters per day. The last term has to do with planetary vorticity. It's quite small at these scales, so we'll just go ahead and neglect that. So let's take a look at, all right, we've got these different terms. What does it look like over an eddy? What kind of upwelling or downwelling pattern does it generate? So if we sum all the terms together, we get over northern hemisphere cyclones, we have downwelling over the interior of the eddy, including the center, displaced a little to the north. And the total Ekman pumping in anticyclones is upwelling, but again, it's displaced. So the question is, why is the total Ekman pumping displaced? Well, the first term, which I mentioned is sort of your standard Ekman pumping term, has a very simple downwelling or upwelling signature. So here we'd see that in the case of an anticyclone, we have the ability to bring new nutrients towards the euphotic zone. And what differentiates this from the eddy pumping term that we discussed just a few minutes ago is that this is happening throughout the lifetime of an eddy. I forgot to say this earlier, but when we have this intensification, this eddy pumping, that only occurs when we have changes in amplitude of the eddy. And the second term that causes this sort of asymmetric monopole is the vorticity gradient term, and that's basically just a dipole of upwelling and downwelling. So if you were to sum this over the life of a phytoplankton rotating around an eddy, if this phytoplankton is rotating around the interior of a cyclone, it's generally going to feel downwelling. And the net movement would be down, because if we look at this term, we have downwelling and upwelling, the net movement's quite small. So if you look at sort of what the net effect is of these terms, it's mostly dominated by the smaller term, which is that of the surface current-induced Ekman pumping. All right, now let's look at some biological effects from this. So what we did is we used a model that Dennis ran of the North Atlantic. It's a 10th degree pop simulation, and it had an ecosystem model coupled to it, the BEC ecosystem model. It's a fairly simple model. It has 3 phytoplankton types. It has small phytoplankton diatoms and nitrogen fixers like diazotrophs. And then it has a very, very oversimplified zooplankton term. So we don't look at top-down controls of this model. It doesn't do it right. It has limited nutrients of nitrate, ammonium, phosphate. And here I'll show on the left, this is just a CWIF's ocean color image in color. And shown above that are contours of sea surface height, which are eddies. And so what we looked at here was in the region of the Gulf Stream, where earlier in the roadmap we saw we have negative correlation, so we expect to see enhanced chlorophyll and cyclonic eddies and suppressed or lower chlorophyll and anticyclonic eddies. Here's just a snapshot from the model. We did quite extensive comparisons. We found that the model, although it does not really reproduce the mean field of chlorophyll all that well, a lot of the perturbations look really realistic. And so we tracked the eddies in the model, we compared that to observations, and we did this sort of eddy-centric analysis. So here are composite averages of chlorophyll anomalies. They've been normalized by the mean field. And what we see here is in anticyclones from observations, we have low chlorophyll in the center, and in cyclones, we have high chlorophyll. So this is what we expected to see from the correlation map. Now, if we go back to the mechanisms we discussed, this would be consistent with eddy pumping, with the uplifting of isopycnals during the formation of cyclones that generate upwelling, and the pushing down or downwelling of isopycnals during the formation of anticyclones. This simple pattern really isn't consistent with the Ekman pumping that I just explained, even though we know it's occurring. So we ran the model in 2 different configurations. In one configuration, we included this eddy-wind interaction, which is the Ekman pumping term that we looked at. In the second configuration, we did not include it. And at first order, they look quite similar. The magnitudes are different, and that's because the mean field of the chlorophyll is quite different. But the spatial structure is quite similar. So it looks like when we include Ekman pumping or we prevent it from being in the model, we don't get much of a difference when we look at it in this way, so in terms of looking at the composite average. But as I mentioned before, we have other metrics by which we can look at how these eddies influence the ecosystems. So if we track eddies and we create composite average time series, so we look at what happens when we first find an eddy, and we look at and we compare its chlorophyll signature as it goes along. So here on the x-axis, we have the age of eddies in weeks. And on the y-axis here in the top panel, we have these chlorophyll anomalies I showed. And if we look from observations, we see positive chlorophyll anomalies in cyclone, shown in blue, and negative chlorophyll anomalies in anticyclone. But you can identify a couple different trends. If we look at the different models in general, they do reproduce the sign correctly. There's some little different bumps and wiggles. But we developed a new metric which we thought was a little more helpful, and that was to look at what happens to the chlorophyll the eddy started with. So when an eddy forms, as I mentioned, it can trap an ecosystem. So we take that and we say that's the chlorophyll at T0. Now we're going to move forward in time, we're going to track it, and we're going to see how that chlorophyll changes. So here from the observations, we see, for example, in cyclones that from T0 we see a couple perturbations, but none of them are really statistically significant. So in terms of significant trends, we don't see any in the cyclones in this region. If we look at the anticyclones, it's quite interesting to see that when we start off, we have a little bit of perturbations, but throughout the first 16 weeks, we start to see a positive trend in chlorophyll. So this is odd, because at first we saw in the composite averages that the anticyclones are generally associated with negative chlorophyll anomalies. But if we look at them as they evolve in time, what we start to see is that they have negative chlorophyll anomalies when they form, but over time they start to get larger. They might not actually become positive or might not be as high as they are relevant to their surroundings, but we do see an increase. So this is sort of what we'd expect from Ekman pumping, and this is the beauty of using this model, right? We can test this hypothesis because it's the only difference between the two models. So if we look at the situation where we had the Eddy-induced Ekman pumping included in the model, and we go down to here, we see that very clearly we see this positive trend in anticyclonic chlorophyll. So as the eddy ages, as it's spinning, as that upwelling continues from the interaction of the eddy with the wind, we start to see an increase in chlorophyll. In the model where we don't include that, we have the opposite trend. So we thought this was really interesting to see that at first glance, we didn't think we saw a difference, just looking at the composite averages or even the correlation analysis, which I didn't detail here. However, when we really dig down a little deeper and we look at the evolution of the chlorophyll signature within the eddies, we see this trend that is quite different between the two simulations. And the simulation that includes eddy-induced Ekman pumping, which we know is a real thing, actually reproduces the trend we see in observations. Okay, so we asked, is this because of nutrient upwelling? Is this for other reasons? Since it's a model, we're able to look at the flux of nitrate, which is a limiting nutrient in these anticyclones. And so what we did here is we looked at the vertical advection of nitrate through the layer at 112 meters. We picked that layer just because it's perennially dark, right? So nitrate probably isn't being consumed there. And the same thing again, we looked at from when we first detected the eddy over the first 16 weeks. If we look at the simulation that does have eddy-induced Ekman pumping, which is shown in black, we see a little oscillation around zero, but over time we see an influx of nitrate into the euphotic zone. So this is evidence of actual upwelling of water that has nitrate into the surface zone that can be made available to the phytoplankton ecosystem. Whereas in the simulation that did not have eddy-induced Ekman pumping, we did not see any evidence of upwelling that was significant at all. So this led us to determine that, at least for the eddies we're looking at in the Gulf Stream in the simulation, it appears that the eddy-induced Ekman pumping is perturbing the chlorophyll field, even though at first glance we don't see evidence of that. So this taught us a couple important lessons, one being we have to be really sort of vigilant in how much we infer from these global maps of eddy effects, or even from the composite average of thousands of eddies. And then it also showed us the power of what we can do with some of these eddy resolving coupled physical biological models when we analyze them in a frame of reference that moves with the eddies, which is something we've really enjoyed doing. It's given us a new sort of approach to looking at this stuff. All right, the final mechanism I want to talk about is the modulation of surface mixing by eddies. So anticyclonic eddies, as I mentioned, at least in the North Atlantic, generally associated with warm water. And so if you have a warm water and a cold air over that, you'll have some heat flux, quite a bit of heat flux. If you had a cyclonic eddy in the same region, which is associated with cold water, the difference in temperature between the atmosphere and the ocean is less, so you have a little less heat flux. So we would expect to see some deeper mixing in anticyclonic eddies versus cyclonic eddies. So what we did is we took all the Argo float profiles, we co-located them to eddies, and we said, what are the mixed layer depth anomalies within eddies? And so we constructed these global maps, and we limited this to the winter when we have the deepest mixed layers, so when we have the largest difference between the air and water temperature. And we see that for the case of anticyclones, we see a fairly general pattern that you usually have a positive mixed layer depth anomaly. And here we define positive mixed layer depth anomaly as a deeper mixed layer than the surrounding. So as expected, we see deeper mixing in anticyclones compared to cyclonic eddies. Now there's quite a bit of noise in here. Part of that obviously has to do with variability and how eddies influence this, but it's also imperfect sampling, right? These are Argo floats, and as we know, there's many parts of the world ocean that are not perfectly sampled by Argo floats. I'd like to go into a little more detail in one particular region, as I mentioned before, and that's the South Indian Ocean, of how this might affect phytoplankton that are inside of eddies. So what's interesting with the eddies that spawn off the Lewin Current that sort of form along the west coast of Australia, go out in the South Indian Ocean, if we composite average their chlorophyll anomalies and we separate it by month, we see this very big seasonal change in the nature of the chlorophyll anomalies. So during the austral summer, the anomaly is small. It's dipole in nature, which is suggestive of this eddy stirring. As we go forward in the year from the austral summer into the winter, we start to see these large positive chlorophyll anomalies in the center of the eddies. The contours I'm showing here are Ekman pumping velocities. So to first order, at least here in July, it looks like they agree quite well. Okay, so we thought, well, what's interesting is why don't we see a response to Ekman pumping during the austral summer, and we do see it during the winter. So we tried to take a look at how the stratification changes in the eddies. And once again, we co-located the Argo float profiles to the eddies. So this is using all the available data we had in that region, and we get a pretty good coverage of the interior of eddies when we look at them in this Lagrangian frame of reference. So here we have Argo float profiles inside anticyclones and cyclones, and from that, we're able to reconstruct the seasonal cycle of mixed layer depth in anticyclones separately from cyclones. And this is where we realized that in anticyclonic eddies, we have much deeper wintertime mixing when compared to cyclones. Now, the region I shade here in green was when we had this monopole of high chlorophyll in the center of these southern Indian Ocean anticyclones. So during that time, we have fairly deep mixed layers. So we were a little stuck with this because we still had high Ekman pumping velocities, but we only had a response during the winter. So a couple other folks, they followed up this work, and DeFoisse et al. Made a very nice example of calculating a nitrate flux due to these different mechanisms inside these South Indian Ocean eddies. So what they did is they took climatological nitrate values, and they just figured out how much nitrate could you flux into the euphotic zone based off of a couple different mechanisms. The first one is this eddy-induced Ekman pumping. So if we look throughout the year, we see a vertical nitrate flux during the austral winter, but it's actually quite small, especially when we compare it to the flux that comes from the deeper mixing in anticyclones. So it looks like in this region, there might be some evidence that suggests deep mixing anticyclones could actually really help to lift isopycnals, not to lift isopycnals, but to bring new nutrients to the euphotic zone. All right, so in summary, the mechanisms so far that we really have described and explored that influence chlorophyll at the mesoscale can be segregated or separated into things that advect ecosystems horizontally, that cause vertical fluxes of ecosystems and nitrate and other limiting nutrients, and those that perturb the mixing structure at the base of the euphotic zone or even in the mixed layer within eddies. Globally, eddy stirring appears to dominate the signal, and our analysis reveals that multiple mechanisms can actually be acting on any given group of eddies in the world ocean depending on time of year. And by combining both satellite and in situ observations, we are now able to estimate some of the impacts of eddies on near-surface mixing. So with that, I'll take a few questions. I'm running a little late on time here, and we'll move on to some of the smaller scale stuff.
Right, thank you. I'm Shu Wenzhang from Rutgers University. Thank you for your excellent presentation. I have two questions for you. The first one is when you turn off the wind in your model simulations, how does the background mean flow changes and the eddy characteristics changes to influence your composite? The second question is you talked a lot about your surface chlorophyll associated with eddies, but we know there are some chlorophyll maximum associated with subsurface water column inside the eddies, like the mold water eddies. So have you taken a look from your model results?
So in response to the first question that asks how different is the flow field when we don't include the surface stress correction that drives Ekman pumping? Well, it turns out that eddy-induced Ekman pumping is one method by which we attenuate eddy energy. So we get smaller eddies of smaller amplitude, and we didn't really look to see how to change the mean surface current field, but we did see that the eddies had smaller amplitude, and that's actually detailed analysis by Larry Anderson from a 2011 paper I'd be happy to send you. The second question, if I understood it correctly, was what about deep chlorophyll maximums? And indeed, and especially in oligotrophic gyres, we see these deep chlorophyll maximums that we generally cannot at all detect from satellites. We saw that in Dennis's work from the Sargasso Sea, where the signature was really deep in the ocean. And I think that's an important part of the story, at least that we're seeing in the South Indian Ocean, where we start to see the difference in the anomalies seasonally. part of that story might be due to mixing, and part of it might just be due to the fact that in the summertime in the South Indian Ocean, we don't see where most of the chlorophyll is from satellites. And we've actually looked at some bioargo floats that seem to support that idea that during the austral summer, you develop this deep chlorophyll maximum that you just won't see from satellites.
So, Peter, when an anticyclone spins down, then the depressed isopycnal gradually comes back up. And so the chlorophyll anomaly, the negative chlorophyll anomaly would gradually fade away. Now, when you turn on your eddy-wind interaction mechanism, it speeds up the spin down of eddies. Mm-hmm. So could it just be that depressed isopycnal is gradually coming back up, and so you are increasing the chlorophyll in time, and essentially it's a spin down of the eddies. Is it the same thing that you're talking about?
Yeah, it's an interesting thought. It's something Dennis and I had talked a bit about because we didn't really know if those are actually separate things, right? Because you have eddy-induced Ekman pumping, which is attenuating the energy of the eddy, which drives upwelling, and you have the upwelling of isopycnals. So I'm sure they're very connected, right? But I don't know if I really understand how to say that those are different, or much rather how to separate them. Because you have the spin down of an eddy, and it looks like much more of that is happening when you include this surface stress correction. Whereas when you don't include it, they spin down slower, and so they have less upwelling. So I think it's a really important thing to think about. And the magnitude of those two upwelling velocities, I think, are quite comparable, right?
It's not that.
No, it's right. We're not talking about mixing here. We're just talking about upwelling. We're moving isopycnals. There's got to be something happens that's dipycnal to get those nutrients out of those isopycnals, right?
All right, this is a great discussion. We can talk more about it after the session. Can we thank Peter again?